Welcome to Summarize Science. Simulating the quantum world of atoms and electrons is one of the biggest challenges in science, crucial for designing new materials and medicines. The problem is that as you add more particles, the complexity of the simulation explodes exponentially. This is why many hope quantum computers will one day provide the answer. But in a fascinating twist, this paper introduces a new classical algorithm that tackles these incredibly hard problems with stunning efficiency. It's called the variational double bracket flow, or vDBF for short. The secret sauce is a technique called sparse polydynamics, which was actually developed to help benchmark and test early quantum computers. Instead of tracking every single possibility in a quantum evolution, which creates an exponentially large problem, this method smartly simplifies things. It focuses only on the most important interactions and truncates, or cuts off, the ones that have a tiny, almost negligible, effect on the final energy. This allows it to get a very accurate answer without doing all the impossibly hard work. So, how well does it work? Let's look at the results for a 100-qubit system called the 10 by 10 Heisenberg model. A standard high-performance method called DMRG took over 50 hours on 64 computer cores to get a benchmark energy. The new vDBF method got a highly accurate result, with less than 1% error, in just about 10 minutes on a single core. That's not just a little faster, it's a monumental speedup. The story gets even more dramatic for a different system called the Hubbard model, which is famously difficult to simulate in 2 dimensions. For a 128-qubit version, the researchers show their method achieved an accurate energy estimate in about 3 hours. In comparison, the best result from the standard DMRG method took over 3 days on 64 threads and had comparable accuracy. So why is it so much faster? This plot shows that the new method focuses on local correlations between particles and lets the long-distance correlations decay away quickly. It's a clever approximation that captures the essential physics needed for the energy, while discarding the complex details that slow down other methods. The researchers also use a clever extrapolation technique, analyzing the trend of their results to predict the exact answer even more accurately. So, let's recap the important points. A new algorithm, inspired by techniques used to test quantum computers, can now solve extremely difficult quantum simulation problems on classical computers. It achieves remarkable accuracy with a speedup of hundreds or even thousands of times compared to established methods for certain challenging systems. What does this mean for the future? It shows that the race between classical and quantum computing is far from over, and that classical simulation still has powerful new tricks up its sleeve. Tools like this could help scientists make progress on problems in materials science and chemistry right now, without having to wait for fault-tolerant quantum computers. Thanks for watching Summarize Science.